Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our second lecture covering material from Chapter 8. Previously, we learned how to write Lewis structures following a very detailed set of rules. So we begin this lecture with a problem. What's the Lewis structure of CO2? And after a brief amount of time, I'll write this structure up. And if we look at it carefully, it appears to be a valid Lewis structure. We have octet on all of our atoms, but it's probably not the one that you came up with. The one on the left over here is more likely what you came up with the two double bonds as opposed to one triple bond. And this happens quite a bit when we're drawing Lewis structures. We get into these situations where we can produce a valid Lewis structure and then another one that it's also valid that looks like it. And you'll hear this term resonance, a resonance structure associated with this. So what we have to do is try to determine which one is the best Lewis structure. So we're going to use this idea of formal charge, and we've got the equation up here for formal charge. So we're going to calculate a formal charge on every atom. And we're going to take the number of valence electrons for that atom minus the number of lone pair electrons. And that means we're going to count each electron. And then we're going to subtract the number of bonds. So each bond is just going to be 1 in this case. So over here on the left, you can see I've got 6 valence electrons for oxygen minus 4 lone pair electrons on that oxygen minus 2 bonds. And this has a formal charge of 0. What we're going to try to achieve for the best structure is formal charges closest to 0. Now, sometimes you'll calculate your formal charges like we did in this case, and all 3 atoms had a 0. But other times, it's not possible that everything is going to be 0. So be on the lookout for numbers like 2 or 3. This typically means that you can draw a better Lewis structure, even if the one you have is valid. So you'll hear this term Electroneutrality Principle, and this has to do with the way the electrons are distributed within the molecule so that the charge on all the atoms is as close to 0 if possible. Now, sometimes we end up with formal charges of, let's say, -1, and maybe we have a -1 and a +1, but we have 2 structures that both share this. This is kind of rare, but when this happens, we can look to electronegativity to see which one gets the -1. So the higher the electronegativity, that one will have the -1 in this case. So pretty rare, but we'll come across it. Here's a couple of examples we did in class. We have, I've kind of left up here the POCl3, and you can see here it's kind of all worked out. We've got the formal charges, again, for each atom, and this is one that worked out to be all zeros. Now realize, if I had a single bond to that oxygen, the phosphorus to oxygen, and you can play around with this, and this would also be a valid Lewis structure, but the formal charges wouldn't all be zeros. So real good exercise for you is to write this structure with just single bonds, and then calculate your formal charges to realize that this one's better. And another thing that's worth mentioning here on this structure, we had 3 atoms in here, and it's kind of intimidating, but in the previous lecture, we mentioned that terminal halogens will only form single bonds, and this can really help you out when you're drawing these Lewis structures. So you can see this compound has 3 chlorines. Chlorine's a halogen, and in this situation, they're terminal. So they're just bonded to one thing. They're kind of on the outside of the atom and or on the outside of the molecule. So I know right away these are single bonds, and there won't be any double bonding occurring here. So it's really worth trying to remember when drawing Lewis structures. Our bonds have properties. Our single bond is the longest bond, like compared to a double bond or a triple bond. The single bond is the longest one, but it also has the lowest amount of energy in it. And I like to think of this like how much energy would it take to break that bond? And so it's easier to break a single bond, or it takes less energy than it would to break a triple bond. Yeah, much like sticks, if you had 3 sticks, it'd be harder to break than 1 stick. So maybe that will help remember that. And there's this thing called bond order. And a single bond has a bond order of 1, and a double bond has a bond order of 2, and a triple bond has a bond order of 3. And we can actually calculate this, and it's pretty obvious for these cases, but I can calculate a bond order by taking the number of bonds and dividing it by the number of atoms that it's bonded to. So for instance, I can take this carbon-carbon bond here, and I can say, okay, I've got 1 bond from carbon to carbon, and it's bonded to 1 atom from the central. So that would be 1 divided by 1, or a bond order of 1, where this one would be 2 bonds, right, divided by the 1 atom that it's bonded to. So 2 divided by 1. And you'll see why this is useful when we move forward. This carbonate ion brings up a real interesting Lewis structure, because we have 1 double bond in there. And it looks like I got really lazy and didn't add my valence electrons, or my unpaired electrons up here. So I apologize for that, but we've got a good one here anyway. So I've drawn my structure. I've done my formal charges, and you'll notice I've got a -1 and a -1 here. Also notice that if I add those up, I get the charge on the ion. It's a 2- ion. Another thing to point out is that because it's an ion, when we're all done, we have to put these giant brackets around it, and these brackets kind of draw attention to it. It's like, I'm an ion, and we'll write the charge in the upper right. So if we didn't have the brackets, you can see how it'd be pretty easy to not realize that's an ion, because we've got formal charges in here and lone pairs of electrons and stuff. So those brackets are really necessary. But back to the point here, I've got a Lewis structure, and the question is, well, okay, I've got a double bond here. Well, could the double bond be down here or here, or could the double bond be here? And so really there's 3 possible structures, all with the same formal charges going on here. So these 3 structures are we call them equivalent resonance structures. And the way we draw them is we draw all 3, and we have to put these arrows, these double-headed arrows in between them. So this is how we would represent this. We'll show the double bond in all 3 locations. So this is nice. It's a little cumbersome, but what's really, really important that you realize is that this does not really exist with a double bond and 2 single bonds. So remember we said that the single bond is a longer bond than a double bond? Well, when we measure the bond lengths for this ion, they're all the same length. And what's really interesting is they're shorter than a single bond, but longer than a double bond. So it's kind of like a hybrid bond, but we can't really draw that. We don't have a scale to draw our single bonds for length, so we couldn't try to draw the bond a little bit shorter to be a resonance, but this works. It gives you a visual, but realize that neither of these is actually correct. So back to this bond order, if I do the number of bonds divided by the number of bonding sites, or the number of bonded atoms for my carbonate ion, each site, let's go back. We've got 4 bonds, 1, 2 with the double, 3, 4, and we've got 3 bonded atoms. So that's 4 over 3, and our bond order is 1.3. And remember, a single bond is 1 and a double bond is 2, and it's between 1 and 2. So further evidence that these are not double bonds or single bonds, but a hybrid of the 2. So we got a couple more examples here, things that you should definitely work on. I've got the NO3, I've got the NO2Cl up. And so we've got the structure here, and we've got our formal charges, and we have, this equivalent resonance situation again, but realize that this chlorine is a halogen, and it's terminal halogen, so this can only be a single bond. This isn't involved with this resonance at all. So when we do these bond orders, we have two. We have the nitrogen to chlorine, which has a bond order of 1. It's a single bond, or I could say 1 bond divided by 1 atom. And then we've got our NO, which could really exist. The double bond could be here, or it could be here. So now we've got 3 bonds and 2 bonded atoms. So 3 over 2, or 1.5 for this one. We've got the double-headed arrows in here. We have to show both. You should really keep practicing this stuff, and try the NO3 minus. That's a good challenging one. It is an ion. Don't forget to put your brackets in your charge when you're done. Check those formal charges. The formal charge is really your guide to make sure you're getting the best Lewis structure. So keep practicing. I'll keep producing. So thanks for watching. Give the video a thumbs up. Subscribe if you'd like to see more from the Professor's DuBois channel.